Have you ever stopped to think about the incredible journey your message takes? I mean, it's a wild trip that starts right there on your phone, zips across the globe, and actually ends at the atomic level, where some seriously tiny technology is about to change communication as we know it. So let's trace that path together.
It really does feel like magic, doesn't it? You hit send and boom, almost instantly, your words pop up on a screen that could be thousands of miles away. But it's not magic. It's actually a fascinating process with a few key players and one major villain that we all have to deal with. Okay, so first, let's map out the epic journey your message takes. The best way to think about it is like a super high-tech delivery service, one that's moving at the speed of light. Believe it or not, every single communication, from a whisper across a room to a satellite broadcast, it all follows these 5 basic steps. It starts as an idea in your head. That's the source. Then your phone, which is the transmitter, converts that idea into an electrical signal. That signal then has to travel through a channel, and then it gets picked up by their phone, the receiver. And finally, it becomes an idea in their brain, the destination. It's this elegant, unbelievably fast process. Now, out of all those steps, the channel is where all the real drama happens. This is the information superhighway. It can be a physical path, like those massive fiber optic cables running along the ocean floor, or it can be wireless, with your message just riding on electromagnetic waves through the air. But here's the thing, no matter what path it takes, the channel is where our hero, the signal, faces its greatest enemy.
And yeah, that enemy has a name: noise. In a world of communication, noise isn't just about sound. Oh no, it's the ultimate saboteur, and it's trying to mess up your message every single step of the way. You can really think of this as the eternal battle of communication. On one side, you've got your signal, that pure, clean information you're trying to send. And on the other side, you've got noise, which is just any random, unwanted energy that gets mixed in and tries to garble that message. So, where does all this interference come from? Well, it pretty much breaks down into 2 main camps. You've got external noise, which is everything happening outside your device, and then you've got internal noise, which is actually generated by the components inside it. External noise is the stuff that's pretty easy to imagine, right? A lightning strike, a solar flare from the sun, even just the engine of a car driving by. But internal noise, well, that's something much more fundamental. It's caused by the laws of physics itself, like the random jiggling of electrons inside a wire. It's called thermal noise, and you literally cannot escape it. So if we can't eliminate noise entirely, how do we build systems that can beat it? The answer is to think smaller, like way, way smaller.
So let's go there. Welcome to the nanoscale. We're about to shrink our whole perspective down to a world where the familiar rules of physics start to get a little weird, and that weirdness offers a totally new way to fight the battle against noise.
Just to get our bearings here, 1 nanometer is 1/1000th of a meter. It's a scale that's, well, it's pretty much impossible to wrap your head around, so let's try to visualize it instead.
Okay, let's start with something we all know: a single strand of your hair. On this new scale we're talking about, that one hair is a colossal 80,000 nanometers across. Now, let's zoom in even further. We're pushing past the hair down to a single red blood cell that's just floating in your bloodstream. Now we're down to about 5,000 nanometers, getting smaller.
And finally, let's dive right into the nucleus of that cell, to the very code of life itself. A single strand of your DNA is just 2 nanometers wide. That is where we are. We have officially arrived at the nanoscale. You know, this whole idea isn't actually new. Way back in 1959, the brilliant physicist Richard Feynman gave this amazing talk where he imagined a future where we could literally manipulate individual atoms. He saw that at the bottom, at the nanoscale, there was this entire new world of possibilities just waiting for us. And boy, was he right, because when you get this small, matter starts playing by a whole new set of rules, and it gains some absolutely incredible new abilities. I mean, just look at gold. At our scale, it's yellow, it's shiny, and it doesn't react with much of anything. But shrink it down to nanoparticles, it can become red or even blue, and all of a sudden it's a fantastic catalyst. Same thing for carbon. At the nanoscale, it can form these tiny tubes that are 100 times stronger than steel. So what on earth is going on here?
Well, one of the reasons for that crazy color change is a phenomenon called surface plasmon resonance. Essentially, and this is the cool part, at this tiny scale, light starts to interact with the electrons on a particle's surface in a completely new way. And that changes which colors get absorbed and which ones get reflected back to your eye. And just like that, yellow gold becomes red or blue.
But the biggest reason things change, the real game changer, is this massive increase in what's called the surface area to volume ratio. See, when you shrink something down, a much higher percentage of its atoms are right there on the surface. That makes it way more reactive. And on top of that, you've got quantum effects that start to take over and dictate behavior. It's a whole new world.
So, the big question: how does this bizarre world of strange, powerful new materials help our little text message in its battle against noise? This is where the two stories finally connect, and we get to see how the future of communication is literally being built from the ground up. It all comes down to the heart of all modern electronics, the transistor. Its entire history has been this relentless march into the nanoscale. I mean, the very first transistor was the size of your hand. Today, we can fit billions of them on a single chip, and each one is smaller than a virus. This incredible journey is what powers our entire modern world. And this, right here, is why all of this matters so much. Nanotechnology lets us build components that are faster, smaller, and way more energy efficient. We can use those super strong carbon nanotubes as almost perfect wires, which dramatically cuts down on that internal thermal noise we talked about earlier. We can use tiny crystals called quantum dots to transmit data with incredible precision, making the signal itself much, much harder to corrupt. We are, in essence, rebuilding our communication systems from the atom up to be stronger and clearer than ever before.
And all of this brings us to a final and really crucial question. Feynman's vision of building things atom by atom? It's not science fiction anymore. It's our reality. This power to design our world at its most fundamental level offers solutions to some of our biggest challenges, but it also hands us these profound new responsibilities. So as we continue to build this future, the real question becomes, what will we choose to build?